Section 3.5, implicit differentiation. So far we've really just looked at functions of the form y equals something, but not all functions are written in this explicit form. Other functions are defined implicitly. For example, the equation of a circle is written as y squared plus x squared equals 25, and that's a circle of radius 5. And you could, of course, solve this for y, and you would get an explicit description as y equals plus minus square root of 25 minus x squared, but it wouldn't be a function because it'd be multi-valued. It wouldn't satisfy the vertical line test. And then there's other equations like y sine of x squared equals x sine of y squared that can't be easily written at all in an explicit manner. And what we want to do is be able to find derivatives for these implicitly defined functions. And to do this, we need a more general method than what we've done so far. And the new method is we're basically going to take derivative of both sides of the equation. And the trick is that y is not a constant. So when you take the derivative of it, you basically take the derivative like it was an x expression, but then you have to use the chain rule and you end up multiplying by a dy dx or a y prime. So let me show you what this looks like. It says, example 1, find dy dx for the function 4x squared plus 9y squared equals 36. Once we finish that, we'll find the slope. But for now, let's just do dy dx. So here's the idea. We write our equation, 4x squared plus 9y squared equals 36. And we're going to take the derivative, d dx, of both sides of the equation. What you do to one side of the equation, you have to do to the other. Now what's the derivative of 4x squared? Well, that's just 8x. The derivative of 9y squared, the 9 will come out in front, just like normal, and then when we take the derivative of y squared, we treat it like it was an x squared. So we get 9 times 2y, that gives us 18y. But y is not x, it is a function of x. So we chain rule on it and we take the derivative of y, and that gives us y prime. And now the derivative of 36 is just 0. And I'll come back to this in just a moment, but let me finish this off first. We now want to get y prime by itself, so we subtract the 8x to the other side. 18y times y prime is 8x, negative 8x. And then we divide both sides by 18y, and we end up with y prime is equal to, here we can cancel, this becomes a 4 over 9, negative 4x over 9y. So that's our y prime, which is the same thing as dy over dx. And it's negative 4x over 9y. Now, in case you were trying to figure out why is d dx of y squared equal to 2y y prime, that's what we got here, right? And the 2 got multiplied by the 9 to give us 18. Consider this. Y is a function of x. So for example, suppose y was equal to sine x. Then we'd be taking the derivative of sine of x quantity squared. Y squared would be sine of x squared. And when we take that derivative, the 2 comes down, and then we have sine x to the 1 power. But then we chain rule and we take the derivative of this sine x to give us cosine x. So what's going on here is that 2 is that 2. Our y is sine x, and our y prime is cosine x. So when we have an actual function, we can evaluate the chain rule like this. When we just have a y, we don't know how to evaluate the y prime, so we just write y prime. And the second part says find the slope at the point 3 over square root of 2 comma square root of 2. This is just going to be y minus y1. Our y1 is square root of 2 equals mx minus x1. That's 3 over square root of 2. And what is m? Well, m is equal to our derivative evaluated at the point 3 over square root of 2 comma square root of 2. Normally I would just say f prime of 4 or something like that, but here I don't have an f. I've got an expression with both x and y, so I have to write it this way. And what this means is I take my expression here for dy dx. Everywhere that I see an x, I plug in 3 over square root of 2, and every place that I see a y, I'm going to plug in the square root of 2. And this simplifies, let's see, that's negative 12 over the square root of 2. And then when I multiply by the reciprocal, this is 1 over 9 square root of 2. So the square root of 2 times the square root of 2 gives me 2, times 9 gives me 18. That cancels to give me negative 2 over 3. So that's my m value. And I get y equals negative 2/3 x minus 3 over the square root of 2 plus the square root of 2. That's my actual line. Sorry, the question only wanted the slope. But this line is important. I'll take the box off of it. It's not an actual answer. Because it actually illustrates sort of what's going on here. So this function, 4x squared plus 9y squared equals 36, is an ellipse. It looks like a circle, but it's sort of elongated a little bit. And we wanted to find the slope of at this particular point. So what does that look like graphically? If I go to MetaCalculator, there's my equation of the ellipse, and there's my equation of the line. And I graph that, it looks like this. So the red is the ellipse. That's my function defined implicitly. Notice that it's not actually a function, it's a graph, but it does not satisfy the vertical line test because it hits in 2 places. And then right here, that's approximately my x value of 3 divided by the square root of 2. It's pretty close to a value of 2. And then the blue line is that tangent line with the slope of negative 2 over 3. So there's actually another way to do example 1. And the idea for this is we can rewrite the expression 4x squared plus 9y squared equals 36. We can first solve for y. So first solve for y. So our 4x squared plus 9y squared equals 36. I can subtract the 4x squared to the other side. And then divide by 9. This gives me y squared equals, let's see, this is 4 minus 4 over 9x squared. And then I take the square root of both sides, and I get y equals plus minus the square root of 4 minus 4 over 9x squared. And it turns out that here, when I'm at the point x equals square root of 3 over 2, well, let's just say the point square root of 3 over 2 comma square root of 2, my y value here is positive, so that means I'm going to take the positive root. So if I graph that, that's this thing right here, it just gives me the top half of that ellipse. If I put a negative in front of it, and I graph that, it now gives me the bottom half of the ellipse as well. So that's how I can solve first for the explicit function. And now, if I want to take the positive root, that's 4 minus 4 over 9x squared, I can rewrite that as that to the 1/2 power. I can now just take the derivative of that directly. 1/2 4 minus 4 over 9x squared to the negative 1/2 times, I chain rule and take the derivative of this stuff on the inside. 4 turns into 0. Negative 4 over 9 stays a negative 4 over 9, and then I multiply it by the derivative of x squared, which is 2x. And this simplifies down a little bit. Let's see, this becomes a negative 8x on top. On the bottom I get this 9 times that 2, which gives me 18. And then all of this becomes on the bottom, because it's a negative, and then a square root because it's to the 1/2. 4 minus 4 over 9x squared. And again, this will cancel, so that's negative 4 over 9, sorry, negative 4x over 9 square root of 4 minus 4 over 9x squared. And it may seem like this is a different answer because before I got negative 4x over 9y. And what's going on here is that this expression right here is equal to my value for y. So it looks different, but it's actually giving me the same thing.